Well, yes, but I'll check because we have get something like that. Also, very sad. Otherwise, if you
Okay, when you're ready. Okay, so yesterday we got through the basics of a leapfrog integrator and shown that because it's exactly reversible, the errors are of order delta tau cubed per step, and order delta tau squared, therefore, for a trajectory of length 1, or fixed step size independent number of units. So we can, however, do better. So I want to now digress onto a particular class of integrators just to show that what you can actually achieve with these symplectic integrators. And it's perhaps somewhat surprising that you can actually produce very simple symmetric symplectic integrators of arbitrarily high order just by combining leapfrog steps in a suitable way. So this is, I'm not sure in practice it's very useful going beyond sort of fairly low orders, but it's amusing that this will work, and it works in practice too. It's amusing as simple as it is. So suppose that we have a leapfrog integrator and we compare it, and imagine that there was an exact integrator that exactly followed the solution of Hamilton's equation, so found the exact classical path with no step size errors. And I'll write that integrator as an operator. You can imagine like smooth functions on phase space. And we'll call that operator e to the delta tau times h hat. So in this case, h hat is basically configured as a differential operator, which is the exact integrator for the exact. But we'll be explaining in much more detail why I call it h hat. Just consider this thing as the exact integrator that integrates our system for a time step delta tau. Okay, and for the moment, just believe that there is such an operator h hat that could do that. And we have a leapfrog integrator. I'm going to call that C sub 1 of delta tau for the moment, just to be systematic. And what we've shown is that this integrator has errors of order delta tau cubed. So I can write this integrator as the exact integrator multiplied by 1 plus delta tau cubed times R1, where R1 is some operator on phase space which gives the error in the integrator. Now, all we care about really is that the R1 produces the leading delta tau cubed error. It can produce higher order error bits as well, but we just lump them all together in the order delta tau for the fifth part, which is still there as well. But the important thing is it doesn't actually matter whether we evaluate R1 at the beginning of a trajectory or the end of a trajectory, because all the differences there are going to be of order delta tau, and therefore, or delta tau squared, and they will therefore contribute to higher orders. And as long as we maintain that the integrator is going to be symmetric, that is reversible, then we also know that the errors, the next error terms are order delta tau for the fifth, there cannot be any errors of order delta tau for the fourth. So whatever we do, we're not going to introduce even powers of delta tau in the error term. So the trick is you consider this integrator, which I call C2, which is supposed to integrate for a step size delta tau again. So you first do a step using your leapfrog integrator of length epsilon1. I mean, the choice of epsilon1 is just going to be something that normalizes the step size, so the total step is length delta tau. Then you do a step of length minus sigma 1 times epsilon1. So for the moment, ignore the subscript 1s, that will be more useful later. So minus sigma epsilon. So I've chosen to put the minus sign explicitly, so that sigma is positive. So what you do is, in other words, you're doing a step forwards, then you're doing a step backwards of a different length, actually a slightly longer length, and then you finally do a step forward again of length epsilon. Okay, so this is manifestly going to be reversible, right? Because each individual leapfrog step is reversible, and I've constructed this in a symmetric way, so that the whole thing is reversible. So now what we can do is we can say, well, let's write that in terms of this parameterization of C1 in terms of the exact integrator e to the delta tau h hat. So from the first term, we get e to the epsilon h hat times the 1 plus the leading error term, which is epsilon cubed times R1. And then for the backwards longer step, I get e to the minus sigma epsilon h hat, that's the exact part, and the correction term is minus sigma epsilon cubed times R1, okay, because the cube is just coming because the errors are not the cube of the step size. And then finally I get the second forward step, the e to the epsilon h hat, again with an error term which is epsilon cubed times R, and all the remaining errors, and to ignore, all add up to order epsilon to the fifth. So now if I expand out this term using distributivity, what I get is that it's an exact integrator, which goes for a step size of 2 minus sigma 1, so there are 2 forward steps of length 1, or of length epsilon, 1 backward step of length sigma epsilon. So the total gives me e to 2 minus sigma times epsilon. And the correction terms, the leading correction term, is just counts as epsilon cubed R1 for the first and last step, and minus sigma epsilon cubed R1 for the middle step. So it goes together to give me an epsilon cubed times 2 minus sigma 1 cubed times R1, and all the remaining stuff is higher order epsilon, and as I just argued before, that means it has to be order epsilon to the fifth. So what I'm left with is, well, if I'm going to insist that I want this trajectory to relate delta tau, so I want this to equal e to the delta tau h bar with corrections. I'm going to now, I want a higher order integrator, so I want the errors to be order delta tau to the fifth. So I can achieve this final equality there if I set epsilon to delta tau over 2 minus sigma. That ensures that the step length of this whole combination ends up being delta tau. And then the clever bit is I choose sigma to be the cube root of 2. So that when you cube it, subtract it from 2, you get 0, and therefore you cancel off the epsilon cubed error term. Exactly.
And here you don't have to worry about the order of h and R1 because commutators would be higher orders than epsilon.
But that's right, all the places like where you evaluate the R1 is all higher order in epsilon, and magically, or 2 orders higher in epsilon. Yeah. So we therefore have an integrator C2 of delta tau, which we can parameterize as e to the delta tau h hat, the exact integrator. So plus errors which are order delta tau to the fifth times some function R2. Okay, which is just some other function on face space. And the errors have to be order delta tau to the 7, with the higher order, and they have to be odd power. So we've constructed a symmetric symplectic integrator. It's, as I said, it's obviously symmetric. It's also obviously symplectic because each individual step is symplectic. In other words, the Jacobian, the measure is preserved by the integrator because the measure was preserved by each individual step. We'll come back to a little bit more detail later. So, just by this trick, this kind of wiggle, we've constructed an integrator which has errors only of order delta tau to the 7 plus step. Now that was fun. So all we have to do is repeat it. So suppose, the way to repeat it, of course, is you come up with an inductive proof, or if you're implementing it in the program, you just write a recursive program to do this, makes it very easy. So what we'll do is we recursively define a symmetric symplectic integrator, which I'll call C sub n, with a step size of delta tau, which is errors of order delta tau for 2n plus 1. Okay, so this was what the subscript 1 was doing on the leapfrog integrator and 2 on the lowest order Campestrini integrator. So let's suppose we managed to construct a C sub n of that sort. Then we can construct a C sub n plus 1 by following exactly the same recipe that we did before. We do a forward step of length epsilon sub n, then a backward step of length minus sigma n times epsilon sub n, and then a forward step of length epsilon sub n again. We substituted the fact that the error can be viewed as the appropriate power of epsilon multiplied by some function, some operator of phase space. Okay, and again, it doesn't matter exactly where you step to evaluate this operator because all the differences are higher order than epsilon. And we just use distributivity collector terms, define epsilon n to be a delta tau of 2 minus sigma n, and sigma n to be the 2n plus 1 fruit of 2. And that arranges, just as before, the leading error term cancelled out, and the trajectory length is just delta tau. So we've constructed an integrator which is symmetric and symplectic and has errors ordered delta tau to the 2n plus 3. So inductively we've shown that this now works to an arbitrarily high order, an arbitrarily large n. And if you're going to program it, it's very easy because we just recursively define it equal to Cn in terms of Cn minus 1, and you end up with n equals 1 by just using a leapfrog integrator. So this is a class of symmetric symplectic integrators whose errors can be made arbitrarily high power in delta tau. Now, yeah?
Sorry, when you were talking about it doesn't matter where you evaluate the errors are, that's sort of theoretical. I mean, if you were actually coding this up, you wouldn't have to evaluate it all. You just have to evaluate.
That's right. You just evaluate the top line. Yes, right. The errors take care of themselves.
So that's merely this decomposition, the top line there that decomposes the.
That's right. This is just the proof that the errors are going to be high order. Yes. Okay. Yes. So really easy to program. It's just a recursive proof. Okay. And plus we have to calculate, roots of 2 in your program. It's not too hard. Of course, there are a few problems, which is that when the step size on these integrators gets sufficiently large, then the integrators actually go unstable. And instead of having errors which nicely oscillate, the errors explode exponentially. Amusingly enough, although the errors explode exponentially, the integrators still conserve energy. But pretty well. But the point is that we'll come. That's how we. The point is that these integrators have an instability for sufficiently large delta tau. If I go to higher order integrators, the maximum step size you can reach before the integrator goes unstable becomes smaller, because if you like, for C2, the leapfrog step backwards is longer than delta tau, and therefore it will break down for a smaller delta tau. Okay, so eventually you don't win very much because you're limited by the maximum step size you can use for the integrator to remain stable. But if you have a system where the step size has to, where your energy conservation has to be really good, so you need then a really high power of delta tau in the error term is useful, and you're not limited by the stability of the integrator, then using a high order integrator will be very useful. Nevertheless, these are not the best high order integrators. I'm not claiming that. I'm just claiming that it shows that you can get an infinite, an arbitrarily high order without very much difficulty. So, to keep you happy this afternoon, I'm writing down a set of exercises which you can program to try and understand how these integrators work a bit better. So the first thing is to implement a leapfrog integrator as a curry method. Well, depending on what language you're using, and if your language supports currying, then you can write it as a
procedure L, procedure leap, which takes the procedure value of the kinetic and potential energy as argument and returns the procedure, which is a function of the trajectory length and the step size. If you were writing in a language like a basic object-oriented language which has classes, then the same effect could be achieved by making the first set of parameters, the procedures giving the energies, as arguments to a constructor, an object in the class. So you get say pointers to those procedures as instance variables, and then you have a method in the class which gives you the integrator as a function of the step size and trajectory length. Okay, but it's just a fun way of splitting up the arguments so that when you're going to do lots of the integrals, you can freeze in the parameters that don't change, and then just have to write down the ones that you're interested in on a more frequent and change on a more frequent basis. So here, the procedures T and B are functions of the kinetic and, well, they give you the kinetic and the potential energies respectively, and they're functions of the coordinates. So P is a decomponent array of the momenta, and Q is a decomponent array of the positions. Okay, so this can describe an arbitrary system with 2D dimensional phase space. So when you've written such an integrator, I presume you also want to specify the initial conditions somewhere. So I'll leave it to you as to how you put those in. So the first thing is that you should verify that this integrator really is exactly reversible, in the sense that it doesn't have any delta tau errors when you run it forwards and then reverse time and go back again. But of course, only going to be exact if you're implementing floating point arithmetic up to a few units of least precision. So in an alt and epsilon in floating point arithmetic, for example, is of order about 10 to the minus 7. In double precision arithmetic, it's about 10 to the minus 14. And it's defined to be the largest floating point number, positive floating point number, that you can add to 1, such that in floating point arithmetic, the result is still exactly 1. So in other words, it's a number which, when you normalize it, or you denormalize it so that the exponent would be back to 1, the actual mantissa shifts off the right-hand edge and the number becomes 0. Okay, so what you can do is you can check that. Then what you should do is measure the energy, the Hamiltonian, which is just T plus V, for, let's say, a set of 10 simple harmonic oscillators, uncoupled simple harmonic oscillators in one dimension, and where the kinetic energy is just a half p squared and the potential energy is just a half q squared. Okay, so we know that the motion would just be circle in phase space, the exact motion. So what we do is then measure the energy before and after a single leapfrog step, and verify that the change in energy over this step, delta H, is proportional to the cube of the step size. Okay? And you could do that by running this thing for a whole bunch of different values of delta tau, and plotting the result for delta H. We plot a log-log plot, so you plot log delta H versus log delta T, and measure the slope of the resulting graph. It will be a straight line, and it should have a slope of 3. So that's the way you can check the order of the integrator really is what it should be. Now, of course, that will only be true if I avoid the regions where delta tau becomes very large, in which case the integrator becomes unstable. Of course, it's still an order delta tau cube, and if delta tau is 1, then any power of delta tau is equally big, and we don't get any useful results. Or if the step size is really small, for example, of the order of an alt, or maybe a few tens of alts or something, in which case the integrator is going to fail because of floating point arithmetic errors. So you should think what you expect to happen when the result has got large rounding errors in it. And whether these results, you could argue that the results, when you've got rounding errors, the rounding errors are going to behave as though they're random, if you do rounding in the appropriate place. So So maybe you would expect the errors to grow like the square root of the set size in a random walk. Or if not, why not? Actually, they don't, but you should understand what does happen there. Okay, so the next exercise was to do the same thing, but now just to take a trajectory length tau over delta tau steps. So just take your step and repeat it tau over delta tau times. So we can, sake of argument, assume that tau over delta tau is an integer, if not round it to the nearest integer or something, and verify that the errors grow like delta tau squared. If tau is of the order of constant over delta tau. So the trajectory length 1. Now, one trick you can do is that when you put a whole lot of these small integrator steps together, you can eliminate all the half steps, so the last half step of one leapfrog step with the first half step of the next one, and combine them into a single leap, okay, value, because both of them, the final half step and the initial half step of the next step, both use the values of the coordinates, the momenta at the end of that first step, which is the beginning of the next step. So you don't have to do 2 steps, you can just multiply the step size by 2, which is why it's called leapfrog, if you think about it. And finally, what happens if you consider this for a much longer trajectory, so trajectories of order length and not 1 over delta tau squared? What do you expect to happen? And you might be surprised that it doesn't happen. Okay, and finally, implement Campestrini, integration of order n recursively, and verify that the suitable step sizes that the error grows like delta tau to be 2n plus 1 for each individual Campestrini step. Okay. So as one comment that I do want to make in this discussion of Campestrini, which is that increasing the order of the integrator is clearly always beneficial if you have a sufficiently large number of degrees of freedom, d, the number of coordinates, because then you need to have a very small step size. The error is usually sort of extensive to the number of degrees of freedom. So you want to have a small error, you have to make delta tau correspondingly small. So a bit like 1 over d usually. So if I have enough degrees of freedom, then I will always benefit from a higher order integrator. But because of the instability in the integrators, it's often better in practice to use a lower order integrator. And in fact, in practice, it's often advantageous to use a lower integrator and just adjust the 3 parameters in the integrator to minimize the cost. So, although making integrators strictly just a higher order is often not the cheapest thing to do in practice. Okay. So, one more exercise in case you still have time on your hands this afternoon or next week or something. It's a useful observation that although symplectic integrators are exactly reversible, exactly area preserving, they're not actually particularly good integrated in the sense of ending up at the right point in phase space. So you'll go somewhere in phase space where the energy is very close to what it should be. To sum energy very well, you might not be following the classical trajectory at all well. And to see what's going on, we could try the following exercise. So just work with d equals 2. So just a 2-dimensional motion of a particle in 2 dimensions. And the potential is basically an attractive gravitational potential, Newtonian potential. So that randomly put 100 in the numerator for the mass. And downstairs I have the square root of the square of Q. Q is the position of your particle, capital Q is the position of some other fixed particles which are trying to attract it. So the potential is an inverse attraction between these 2 bodies, and you can put these heavy masses trying to attract it at coordinates 2j plus 1. So they lie along diagonal in this two-dimensional space. You can choose a direction, let's say, of 6 or something to begin with. Start off at the origin with an initial velocity of 4 units at an angle of 17.5 degrees from vertical or horizontal, it doesn't matter, it's just symmetric. I don't think it's particularly important that you don't have to be very exact about this angle or anything. It's just a reasonable starting point. And then plot the distance in phase space, so the square root of p squared plus q squared. So not only the distance in where you end up in the positions, but also taking account the difference in the momentum at the end. From the true endpoint of the classical trajectory. Then you don't know the true endpoint of the classical trajectory, but you presumably approximate it quite well by doing a run with a sufficiently small delta tau. So do a run with a smallish delta tau to find out where the system ought to go, and then have a look at where it does go as you increase delta tau. And again, you can look at the slope and logarithmic plot to see how far rapidly it moves away from where it ought to be. And in fact, this is not a, you'll find that you just end up nowhere near where the solution's meant to be once you've gone near to one of these planets or whatever they are. So you can imagine you're on a spacecraft going around these planets lying in a straight line. As soon as you have a near collision, then you'll get big forces and you're thrown off course unless you're a very small step size. And what's interesting is that the system is essentially chaotic, which means that if you make a very small change in the initial conditions, you end up in a very different final place as long as your trajectory is long enough. So, although the principle communicates exactly, first of all, in practice, it's really hard because you have to use very high machine floating point precision to really get rid of these big changes when you're a very, very small change in initial condition. And second, it's probably pretty useless because in the real system, if you're trying to calculate this, any small errors in your initial velocity and initial direction will mean that your prediction, where it ends up at the final time is almost totally random. Okay, so there's not too much point actually being able to simulate a chaotic system exactly. But this is a nice toy example where you can see all these nasty things that can happen. Good. Well, so now at the halfway point of this, so I'm going to switch back to doing a bit more maths. So what I'm going to do now is give you a very brief introduction to some differential geometry, because what I want to do later is going to be most easily expressed in terms of differential geometry. I mean, of course, I could still write everything in terms of derivatives and coordinates, but it becomes really messy. And if I write it in terms of differential geometry, it sort of picks out the important ideas much more clearly. So, as I said, there are two reasons for using modern differential geometry in general, not only for symplectic integrators, but for discussing motional manifolds and behavioral properties of manifolds. The first, if you like, is the quote real reason, which is that if you want to describe mechanics on a manifold for which there is no global coordinate system, so for example, a circle, you can think there's a coordinate system theta, but there also has to be a jump when you get to 2 pi. So in the usual angular coordinate system of a circle, a smooth function is kind of hard to describe because the point theta equals 2 pi is in fact the same point as theta equals 0. Okay? Now that's more obvious if you think of a two-sphere, where you can't have a coordinate patch globally. You can get away with one coordinate patch over the South Pole, just to the north of the, say up to the Tropic of Cancer, one coordinate patch centered on the North Pole going down to the Tropic of Capricorn, so they overlap on the equator. And then everything is smooth, the coordinates are well defined, no singularities anywhere, and you can say that there's a smooth, well defined coordinate transformation in the patch where they overlap around the equator. But you can't get one coordinate system which has no singularities. It's got the same problem as a circle, except it looks even worse. Okay, there's somewhere where your coordinates go singular. So latitude and longitude being a good example, they go singular at the poles. So you could even go and look at this one, legal manifold. Well, S1 is a legal manifold, S2 is a S3 is a legal manifold as well. But there are lots of interesting manifolds which have non-trivial topologies, which need more than one coordinate system to describe them smooth way everywhere. So that's the real reason people use differential geometry. They want to be able to do global objects. The second reason is that, which is probably more important from our point of view, is it allows you to describe geometry in a coordinate-free, kind of natural way. You introduce quantities which are naturally defined in the global sense on a manifold. And these allow for kind of more elegant, simpler formulation of things. Okay, you could always write everything in terms of coordinates. If you look at old books on differential geometry, general relativity, things like that, they'll tend to do that, but they get very messy very rapidly. And it's also easy to write down quantities which don't actually make sense globally. So restricting yourself to these abstract concepts which do make sense globally makes it easier to write down things that are meaningful in a sort of geometric sense. So with that motivation, I'll start off by telling you the definition of a differentiable manifold, or a smooth manifold. It's a topological space, I guess. Some concept of space, right? And it has a set of local coordinate systems, which are technically called charts, which are defined on some family of open sets which cover the manifold M. So it might be an infinite number of these. If we have a compact manifold, one doesn't go infinity or something like that, then you can always manage a finite set of charts. And the idea is that these charts must be consistent on their intersections. So just like the example I gave of the coordinate system of a sphere, we have one of the north, central and north pole, one central and south pole. These two coordinate systems, there must be a smooth differentiable transformation of coordinates around the equator in the open patch where they overlap. You see, actually talk about a smooth differential mapping because this is a mapping between, on the case of sphere, between R2 and R2. Right? So you compare a pair of coordinates in one coordinate system, a pair of coordinates in the other coordinate system. So I know what I mean by differentiable. And so I'm not, I don't know what it means to be differential for abstract pointing sets, but I do know what it means to be differential and smooth between coordinate systems. So that's the way that one gets the smoothness into the structure. Okay? And a collection of such compatible charts is called an atlas. Okay, so that's a differential manifold. It's this topological space together with a set of consistent charts, an atlas, which allows us to define smooth quantities, differentiable quantities. Now, if you consider at a given point in the manifold, a space spanned by linear differential operators d by q. So q is locally a coordinate system. So I can define the differential operator, the linear differential operator d by dqi, which, if you like, I would think of as being a vector pointing in the direction of the qi crescent axis. Okay, you think it's something which moves the function an infinitesimal amount in that direction. And if I have a finite dimensional space, in a d-dimensional space, I can have d independent qi's, exactly, no more, no fewer, in my coordinate system. So I have a set of d independent vectors, d by qi, that I goes from 1 to d. And I can think of these as forming a vector space, because I can form linear combinations of them, and the linear combinations are still linear differential operators, which just points in some direction. So this vector space, spanned by these basis vectors, d by qi, is called the tangent space to the manifold at the point x. And here it's write as t sub x of m. And this vector space doesn't matter which particular coordinate system you start off with, they're all just a different choice of basis for the vector space. Okay, so the important thing to understand here is that we're viewing vectors are defined to be linear differential operators. They behave like vectors, they smell like vectors, so they are vectors. That's what we mean by vectors. Okay, now of course, if you have a vector space, there's always a dual vector space. Sometimes you don't think this to be different from the original vector space because in finite dimensions they behave in exactly the same way that isomorphic as vector spaces. But the dual space technically is defined as a space of linear functionals. So they're mapped from vectors to numbers. Okay, and we will call these dual vectors to tangent vectors. We will call them one forms. So regions that are obscure, but hopefully will come clear in a minute. And they live in another vector space, which looks very much like the first one, but we'll just call it something different, and we call that the cotangent space. And we denote that by T star at X to the manifold M. Okay. Now, since the tangent vectors change smoothly over the manifold M, okay, so if I move X to some nearby point, then the derivatives that are given coordinate is going to just change smoothly over that move, because my coordinate system is smooth. I can, the collection of all the tangent spaces over the manifold, so that involves going across and changing which coordinate paths you use in the intersection and so on. That is called, that is also a smooth manifold, which is called the tangent bundle. So T of M. So we just sort of take all the vectors at all points. Okay, and it's all, everything is nice and smooth and differentiable. So this defines itself a nice smooth differentiable manifold called the tangent bundle. And likewise, the collection of all the cotangent spaces is called the cotangent bundle, T star. So, for example, in Hamiltonian dynamics, the velocities, q dots, naturally live in a tangent bundle. Right, they're vectors. But the momenta are actually live in a cotangent bundle. They're dual vectors. They look like vectors, but formally they are cotangent, one forms. Now, in physical terms, what we call the space, this kind of bundle manifold, the space of all Q's and P's, we'll call phase space. So phase space is just a physicist's name for what the mathematicians would call a cotangent bundle. Okay. So, we've already identified the differential operators d by dqi with basis vectors in the tangent space, and we generalize this idea by defining a vector field as opposed to just a vector at a point. And the vector field is globally defined quantity on the manifold, not singular anywhere, and it's defined basically to be a linear differential operator with arbitrary coefficients. Okay? The important thing is that locally it can also be expressed in terms of these bases of derivatives, vector coefficients, and then you have to extend it to the whole space by making sure they're consistent vectors in the overlaps. But we can now talk about global vector fields, and what they are is just linear differential operators. And it doesn't matter which basis vectors you use. So you use basis vectors to define them, but then you can abstract them away. Locally, you can always think of expanding in terms of basis vectors, but globally, it's just a linear differential operator. So that's what we mean by vector fields. Okay, so I think we've probably got to pass through a difficult bit there. So what this means is that if I consider two vector fields x and y, the product of these two vector fields is in general not a vector field, because in general it's got second derivative terms in it. And I said that the vector field has to be linear differential operator, otherwise it wouldn't be a vector, right? It's not linear, it's not a linear space. However, it's useful to note that the commutator of two vector fields, which is defined as xy minus yx, is a vector field because all the second derivative terms cancel. So there's a natural antisymmetric product of vector fields defined in this way by the commutator. Now, a little bit more terminology. When we have a smooth function on the manifold, so just mapping from the point of the manifold to a numerical value, we're going to call those zero forms. So remember, the cotangent vectors, the duals to the vectors, were called one forms. So the functions are just called zero forms. And so I'll use the term smooth when I talk about smooth functions and zero forms, they're the same thing, just different language. The dual space to the linear functionals, so if you consider the linear functionals that take a vector field into numbers, they go more into a zero form. So given a vector field, something that maps that vector field into a zero form, so into a smooth functional manifold now, it's called a one-form field. So it's a dual space to vector space of vector fields. And the local dual basis, so the basis for this space of one forms locally, so locally we have a basis for the vector field given by the d by dqi's, and the dual linear functionals, or what we call differentials, we call dqk, and they satisfy the relation that dqk takes this vector d by dqj into delta jk. So dqk doesn't mean anything mysterious or infinitesimal, it's just a linear function, it's just a map that takes a vector into a vector field into a function, into a zero form. Okay? And again, this set of dqk is just defined locally in some coordinate system, but they do form a perfectly good basis locally for the one-form fields. And more generally, we can consider any multilinear map from a set of vector fields and one-form fields into numbers, and we'll call that tensor fields. Okay, so just like the one-form fields were linear maps from vectors to numbers, sorry, from vectors to zero forms, any multilinear map from any number of vectors and one forms into zero forms, we will call a tensor field. Okay. Now, in particular, the totally antisymmetric linear maps from K vector fields into, I shouldn't say numbers, I should say to zero forms, functions, are called K forms. Well, I'm sorry, to numbers is correct, they're K forms, from any number of vector fields to zero forms. Fields is called a K-form field. So in other words, if omega is in the space of K-forms, K-form fields, so omega maps a bunch of vectors in each giving a tangent bundle, like so each one is a vector field, and it maps it to, let's say, the real numbers, the values functions take, then omega evaluated at x1 through xn, which is just a function, is antisymmetric. So I swap any two of the x's, I just change the sign. So these, basically, these are tensors with all the indices, you know, the way you might use to think of it, all the indices downstairs. So that means that they're functions of vectors and not of all. And in this case, they'll just be totally antisymmetric such tensors. And the algebra of such antisymmetric forms is very useful because there, first of all, there's a natural antisymmetric and dissociative product called the wedge product. So we'll have two K form and an L form, then the wedge product of the two is antisymmetrized and becomes a K plus L form. The surprising thing is that you can find this in such a way that it is associative. So it's a little analogous to the cross product of vectors in 3 dimensions, except that the cross product is not associative, which always confuses people. But this antisymmetric product is like, it's actually the cross product is a dual in 3 dimensions of the wedge product. The wedge product, if you like, of two vectors, two one forms, is a 2 form. And the dual in 3 dimensions of a 2 form would be a 1 form. But that extra dual means that you lose associativity if you try to view it as a map from 2 vectors to 1 vector. So just viewing it as a mapping from 2 1 forms to 2 form, then that associativity is preserved, makes it much nicer. There's also a natural derivation, a natural derivative acting on forms, which is called the exterior derivative, known as d. And for the moment, all I'll say is that if you have any zero form, f, so a functional, smooth functional manifold f, then the one form, the exterior derivative of f, is defined by action on an arbitrary vector field, x. I say that df acting on x is exactly the same thing as x acting on f. Remember, x is a linear differential operator, so it makes sense to say that it acts on a function, a particular function. Okay. So for a one form, theta I define the exterior derivative d theta as a two form, and I define it the following way. I say it's x, well, that's a vector field, so it can act on a function. The function I'll choose is theta of y. Okay, y is a vector field, theta is one form, theta of y is therefore a zero form function on the manifold, which x can act on to give me another zero form. So I define d theta of x and y to be x theta of y minus y theta of x to make sure it's anti-symmetric. And then mysteriously, I also subtract theta of the commutator of x and y. Well, the commutator is a vector field, so that's fine. So certainly the last term is also a zero form field. So well, why do I have this extra term at the end? Well, the reason is that I do this in order to make sure that d squared, if I apply d twice to something, I always get 0. And the proof that that works is I consider d squared f, so f is a 0 form. So d squared f is a 2 form, so d takes k forms to k plus 1 forms. So d squared on f of x and y, where x and y are two arbitrary vector fields. So first of all, let's take the definition from the bullet point. The current bullet point, which tells me what the exterior derivative of one form is, this gives me x on df of y minus y on df of x minus this extra term is df of the commutator of x and y. And then I replace df by of y using the definition of what of a zero form was from the previous bullet point. So I can write df of y is just y applied to f. So I get x acting on y on f minus y acting on x on f minus the commutator of x and y acting on f. And now you notice that that's actually 0, but I need the commutator term to calculate the first two terms combined to give me a commutator. So if I happen to work on an ordinate basis where the vectors x and y commute, then of course I don't need the commutator term because it's 0. But if I chose two vector fields which are not just d by dq's but have some arbitrary functions, coefficients, then the commutators wouldn't vanish because the derivatives of coefficients are not 0, and so I need to correct for that by defining this commutator term in the exterior derivative. And the fact that we've defined, and I will continue to do this for 2 forms, 3 forms, 4 forms. In fact, we will come across the formula for 2 forms because we need that later. But in general, what we always do is we define these such that d squared is equal to 0. And without going into too much detail, if we have an operator of this form where d squared equals 0, and d maps you from objects which have a label k, as in k form, to an object with a label k plus 1, and okay, so d takes k forms to k plus 1 form, this gives us a structure known as a cohomology, which is very important in algebraic topology, classifying spaces and so on. It's called a cohomology, and the homology merely means that the index increases rather than decreases, which is the homology. Otherwise, homology and cohomology are basically the same thing. Okay. So that was a very fast introduction to differential geometry on manifolds. But now let me specialize this to symplectic manifolds, the sort of manifolds which we have can construct Hamiltonian dynamics on. And in Hamiltonian mechanics, a very special role is played by what's called the fundamental two-form, usually called Oega. And this fundamental two-form is always closed, which is the homological language for saying that d omega equals 0. So the exterior derivative of omega must be 0, and omega must be invertible. I'll say what that means in a minute. So on a simple flat manifold, as we've been discussing so far, the choice of omega is almost always dq wedge dp. Okay, dq is on a flat manifold is globally defined as one coordinate system. So dq forms a basis for one form of fields. dq also forms a basis for one form fields as a wedge product. I get a two form field. And the exterior derivative is going to be closed because if I apply d to dq wedge dp, I go get d squared q wedge dp minus dq wedge d squared p, and d squared is 0. So just give me 0, so it's closed. However, there are many interesting systems, constrained systems, if you want to put dynamics, Hamiltonian dynamics onto a circle or onto a 3-sphere or something, then you will actually choose a different fundamental two-form. because dp, well, dp isn't a problem, but dq tends not to exist today, isn't it, global coordinate system? Okay, so we're not going to particularly consider those systems, but we are going to use this abstract language because it's a nice way of describing Hamiltonian mechanics. So, now, this is an important definition. If we're given any smooth function on phase space, so any zero form, and let's call that A, there's a corresponding Hamiltonian vector field, which I will call A hat. So A hat is a vector field, A is a function, right? And it's defined such that dA applied to an arbitrary vector field X. So dA, A is a smooth function, D is the exterior derivative, so that gives me a one-form field that acts on a vector field X to give me a zero form. On the right-hand side, I only go on A hat and X, only gets a two form, so each two vector fields, A hat and X are both vector fields, so it also gives me a smooth function or zero form field. So by equating the two, and using the fact that I'm consistent that only gets invertible, so I can solve that, means that just that I can globally solve this equation for A hat. I've defined a vector field, A hat, for every smooth function on phase space. Okay. Of course, there are many more vector fields than there are smooth functions. Having a vector field, think about it as d coordinates. So you might think that in some sense there are d times as many vector fields, but so there's a very special class of vector fields. Okay, most vector fields are not Hamiltonian, but for each smooth function there is a vector field, which is the Hamiltonian vector field, if we have this fundamental two form. So we need this extra structure. Notice I haven't introduced Hamiltonian function at all yet. So it's only really like, you think about it, it's natural anti-symmetric structure of Poisson brackets. Okay, and that's a very important ingredient in classical mechanics. It's not just the Hamiltonian itself that's important. So let's consider on a flat manifold, let's keep things simple, the exterior derivative dA of the zero form F is the one form, and I can expand it in the local basis to Q and dP of the one form. So it's the A by dQ I try and dA by dP. So in this case, the exterior derivative is kind of a gradient operator. Okay, it's like del. So it's not something that I'm familiar. And the arbitrary vector field, I'm just saying, well, I can also expand it in terms of the basis vectors d by dq and d by dp with some arbitrary functions as coefficients x sub q and x sub p. Okay. So dA x, so I apply dA to x, and now remembering that dq acts on vectors, it doesn't care about the coefficient xq, but it acts on the d by dq, and so I act with dq on d by dq, I get 1, if I act with dq on d by dp, I get 0, and so on. So what that gives me is dA by dq times xq plus dA by dp times xp. On the right-hand side, on the other hand, only with A hat and X, means I've got to act with a two-form field, dq wedge dp, and I've got to act on the vector field A hat of q times d by dq plus A hat of p times d by dp. So A hat of q and A hat of p are functions, zero form, which I'm trying to define by from this relation. And the second argument is just x, again expressed in local coordinates. And so the dq, well, that dq can act on the d by dq of the first argument, leaving me with 1, so I get that from A hat q, and then the dp would act on the second argument, and then if dp acting on d by dq is 0, but dp acting on d by dp gives me 1, so that just gives me x sub p, so I get A hat of q times x sub p. But I could also apply the dq to the second argument, and the dp to the first argument with a minus sign because it's anti-symmetric. So I get minus A hat p times xq. Okay, because the wedge product is anti-symmetric, so I swap the elements around with a minus sign. And now I can equate the coefficients of xq and xp because they were arbitrary functions, but x is an arbitrary vector field. And that tells me that A hat of q is going to be equal to dA by dp, and A hat of p is going to be minus dA by dq. Okay? Which is what I've written in the top line there. So A hat is just a vector field whose coefficients of dA by dP is the coefficient of d by dq, and minus dA by dq is the coefficient of d by dP. So the sort of, we've got the anti-symmetry in the P's and Q's swap over due to this fundamental truth form. Now, if we take a special case of this where our zero form is a Hamiltonian function of phase space, then I get the Hamiltonian vector field. Okay, it's a very special case of a Hamiltonian vector field coming from this special function called the Hamiltonian, which so far can be any zero form, right? We just choose on to be the Hamiltonian. Then this operator H hat, this Hamiltonian vector field, H hat is dH by dP times d by dq minus dH by dq times d by dP. And if you consider a curve, that is just a mapping from the real line into the manifold, so it's got coordinates q of t, p of t, where t is a parameter, time parameter, if you like, that parameterizes the curve. So this has to be a smooth curve in the sense you map into the manifold, and the coordinate, the mapping from t to the coordinates is a smooth, is a differential function. Then we claim that the classical trajectory of the system satisfies the equation that the time derivative c, that's a vector, a conventional operator, so d by dt along the curve c, is always tangential to the Hamiltonian vector field. So in other words, what we've got, talking about Hamiltonian, we use the fundamental truth form, we've got a vector field defined in the manifold. You consider this as a sort of arrow at each point in phase space. And then we integrate this to find a trajectory, which is a curve such that the tangent vector of the curve is always equal to the corresponding arrow you have on the Hamiltonian vector field. Okay, and that defines the classical trajectories. So this system defines classical mechanics in terms of Hamiltonian vector field by saying that motion is always moving in sort of the integral curve of this Hamiltonian vector field. But for that set of equations for that, just getting that q dot is h hat of q, which is dh by dp, and p dot is h hat of p, which is minus dh by dq, which we of course recognize as Hamilton's equations. So we're back to the usual coordinate version of Hamilton's equations. But now instead of doing a set of equations to solve, what we say is if we can find this Hamiltonian vector field, that's basically the solution of classical mechanics for all starting points. Because wherever you start in phase space, you just follow the integral curve of this Hamiltonian vector field, and that defines the classical trajectory. Okay, that's probably a good place to stop for our break. Hopefully, coffee waiting outside. Coffee? Too much math. Yeah. Well, you have to tell me what's the fundamental truth. Yeah. Yeah. So I can check the truth. More of no, just define the main that could be made. Right. That's that fundamental.
So you just get an extra piece. I mean, like you say, it's natural for
Natural from group manifold.
Yeah.
But other cases you have to put it in my
So the way to introduce it, or even just a circle.
For subtle group manifold too.
Okay, so
the point is that there is a work by d theta. D by theta is well, just theta.
right. So is there always choose here then? Is there an easy case to use that?
That's a good question. I presume there is, but I don't know. I haven't looked at these guys.
Yeah. You could imagine his particles moving around. Well, what do meteorologists?
Well,
You know,
yeah, so the base station was a two-state, so we could take it back to another two-state.
Yeah, yeah.